Today I wanted to finish study of Laplace equation, and today is a solution of Dirichlet problem. In fact, the complete study of the Dirichlet problem in any method requires some work related to function theory, functional analysis, and so on, so things which are beyond this elementary course. So I just explain how it is done, and without detail, if you don't mind. We had already plenty of detail, and now I want to somehow collect it in this last topic. So suppose we have domain V, gamma is the boundary, and the problem is Laplacian U equals F in V, U on gamma equals G. So first thing, how to solve this? We first continue the function f outside of gamma as well as a continuous function. Let us construct function f twiddle of x such x in Rn in the whole space such that f twiddle of x equal f of x for all x in V. So inside is the same, and f twiddle of x equals 0 for modulo x more than some large R. Now, how to do it? If we have, say, a function which is given on a segment, some continuous function, like this, then we can do it as follows. We take the value of the function and the end point, and then continue it as linear function. For example, like this, here and here, and further it is 0. If you have this domain, any domain, we can do the following. We draw the lines which are, say, orthogonal to the boundary, yeah? And on each of these lines you have a similar situation. Here is, we are in the domain V, this is gamma, it is a section of by some line, and here we let it go to 0. It's enough. So do it along each of these lines, and we have a function which coincides with function f inside domain, and here outside this strip it is 0. So it is the first thing. So now we work the function in the whole domain, and they solve the equation Laplacian U equals f twiddle in the whole Rn. We know how to solve this problem, solve this equation. U of x equals integral over Rn k of x minus y u of y dy. Here k is fundamental solution. K of xy equals 1 over 2 pi logarithm distance between x minus y if n equal 2, 2 minus n omega n model x minus y 2 minus n more equal than 3. So it is a familiar fundamental solution. And we know that u of x obtained by this formula satisfies this equation in the whole space Rn, and in particular inside domain D. Second, let us find this function u let me call it v. Yes, let us define v of y when y on the boundary equals h. Third, consider inside domain D the function u of x equals v of x plus w of x. So, Laplacian u equals Laplacian v plus Laplacian w. And it should be equal f. Laplacian v in D equals the same f. Not is equal f twiddle, but f twiddle in D equals f. Yes? So this means that Laplacian w equals 0 in D. Laplacian w equals 0. Now what is on the boundary? On the boundary you have v plus w, u on the boundary, v on the boundary plus w on the boundary equals u on the boundary g, v on the boundary is h, g, it is this, equals h plus w on the boundary. On boundary, yes? So, w on the boundary equals g minus h. That's it. So if you find solution of the problem Laplacian w equals 0 in D, W on the boundary equals G minus H, then U equals V plus W is a solution of Dirichlet problem. Yeah. So we reduce it to the problem for harmonic function. So the problem is find the harmonic function such that it takes given boundary values on the boundary. Now for our convenience, let us change notations to the previous one. Laplacian U equals 0 in D, U on gamma equals G. Yeah. So, how to solve this problem? We had, there exists one thing which is called Dirichlet principle. Dirichlet principle. The Dirichlet principle sounds the follows. Consider the let me introduce. So, function is a name for correspondence for any number, say, on the line. We have its value. For any value of argument, we have the value of function. Now, if the argument is a function itself, it is called functional. So, function f of u, for example. So, u is a function, and f of u is some quantity depending on the function. So, functional is a function whose argument is a function. It also is a function. So, yes. So, consider the following functional. F of u. First of all, I have to describe the domain of this functional. Let us denote by, say, A is the set of all functions u in C1 of D such that u on gamma equals f. So all the functions such that they assume the value f of y, g, I'm sorry, this g. Not to be confused. And now for any function of a, we consider the following quantity. F of u equals integral over d 1/2 module gradient u square dx equals integral over d 1/2 du dx1 square plus and so on plus du dxn square dx. So integral, this is called Dirichlet integral. Integral Dirichlet. And consider all the functions, and suppose some function w of x in A gives a minimum to the functional f. So f of w less or equal than f of u for all u in A. Suppose we found the minimum of this functional among all the functions in this class, all the functions which have given values on the boundary. Then Laplacian w equals 0. So this is the Dirichlet principle. So let me prove it. Let w of x be the minimizer of f of u in A. Yeah? And let us consider the function wx plus epsilon vx. Yes, where epsilon is some small, and vx is equal to 0 on gamma. So, no, suppose this is the graph of the function w x, and this is the graph of the function w x plus vx, and vx is what we added. Yeah, so this function should be 0 on the boundary. This is gamma, and this is d. Yeah, and consider the Dirichlet integral of this function. So, Dirichlet integral of the function w plus epsilon v equals integral over d module gradient w plus epsilon v square dx, no, 1/2. Let us expand it. Equals integral over d. What is here? 1/2 module gradient w square plus now gradient w times gradient v 1/2 times 2 gradient w dot gradient v plus 1/2 I'm sorry, it is epsilon, so here epsilon epsilon square module gradient v square dx. Yeah? Equals integral over d. We know what is this. It is f of w plus this is epsilon square f of u v and plus epsilon integral over d gradient w dot gradient v dx plus epsilon square times f of v. And let us f of epsilon. So all this depends on epsilon. If w and v are fixed, what remains is epsilon, parameter epsilon, f of epsilon. If the function w is minimizer, gives minimum, then this function f of epsilon has has minimum for epsilon equals 0, and this is a quadratic function. You see, there is some one constant, there is other constant, there is also constant. So it's just quadratic function. So this means that f prime of epsilon of 0 equals 0. So what is f prime of 0? F prime of 0. So this is constant, its derivative is 0. There is epsilon squared times something, some constant, so its derivative at 0 is 0. Remains this, equals integral over d gradient w dot gradient v dx. And so this is and this is 0. Yes, because w is a minimizer. F of w equals minimum. Let me write this. And now we want to analyze this integral. integral over d gradient w dot gradient v dx equals what? Let us integrate by parts. Minus integral over d Laplacian w dot v dx and plus integral over gamma dw dn v ds of y v y ds y. Now v is 0 on the boundary, yes? So this is 0, so this is 0. Equals v on gamma equals 0. So it remains this. So we have integral over d Laplacian w dot v equal 0 for any v such that v on gamma is 0. Now this already means that Laplacian w is 0. No, let us assume that Laplacian w is continuous. Is continuous. It is, in this case, it is simpler. In this case, it is simpler. If Laplacian w is continuous, suppose Laplacian w is more than c at Laplacian w is not identically 0. Then Laplacian w of some x 0 more than 0 for some model Laplacian w for some x0 in D. Suppose that it is not identical 0, somewhere it is not 0. If it is not 0, so it is either more than 0 or less than 0. If Laplacian w of x0 more than 0, then Laplacian w of x0 equals c, more than 0. Yeah? Then the function is continuous, so there exists delta such that Laplacian u of x more than c over 2 for model x minus x0 less than delta. Okay. And now let us take the function v of x equals phi delta of x minus x0. So this is x0. So here the function Laplacian w is positive, more than c over 2. So if you multiply it by this function phi delta, then the result will be positive. Result will be more than delta over 2. Then integral Laplacian w of x v of x dx more than c over 2. No, the same if Laplacian w x0 negative, so it will be less than minus c over 2. So similar for Laplacian w of x0 less than minus c, less than 0. No, this means that if you assume that Laplacian w is not identically 0, then we cannot have this equality for all v, satisfying this boundary condition v on the boundary is 0. So this means that, so hence Laplacian w equal 0 identically in V. And now we have, this principle Dirichlet principle is stated. Now here are some more subtle points which I do not talk about. The principle is this. It is how Dirichlet himself did it. Now, the question is how to find or how to prove that this minimum is achieved. Because we know that there exist some functions which are positive, the Dirichlet integral is positive, but they cannot achieve the minimum. The minimal point does not exist. So we have to show some procedure of minimization. Fortunately, we have this procedure. We have, in fact, there exist different ways how to prove the existence of minimum, and I'll show one which I find most beautiful. Consider the case, first case, when D equals ball, say with center of 0 and radius r. And we, in this case, we can find the solution explicitly. So we are solving the problem. Laplacian u equals 0 in T. U on the boundary is G, yes, of y. And then we know solution. Solution is given by the Poisson formula. U of x equals integral over sphere of 0 r h of xy g of y dsy, where h of xy is h of xy equals 1 over r, I think 2 over r, r square minus x square, module x square, divided by module y minus x to the power n. So this is the formula which gives us solution. As we studied before, u is automatically harmonic function and assumes the value g of y on the boundary. So we have solution here. And if it is a harmonic function, so I proved that harmonic function, if a function is harmonic, then it gives minimum to Dirichlet integral. No, I proved that if a function gives minimum to Dirichlet integral, then it is harmonic. And now we can follow this chain of equalities back and prove that if a function is harmonic, then it gives minimum to Dirichlet integral. So this means that minimum is here. It is given by this formula. This function u of x is minimizer. Now consider another. We can also consider the ball with center at any point, not 0, but any other point, and the formula will be the same. And now the decisive step. Consider domain which is union of two balls. These balls can be even of different radius. So this is ball, this domain. Let us call it D1, and this domain is called D2. And this domain is D. And I also call this boundary of the first domain D1, I call it gamma 1. It is gamma 1. It is this part. This part, let me take color. So it is gamma 1, and this part, let me call it gamma 1 prime. This is called gamma 2, and this is gamma 2 prime. That's it. And so, assume that the boundary condition is given on gamma 1 and on gamma 2. So we are solving our problem in domain D, which is union of these two balls. start from the function u0 of x is arbitrary function of A. So it satisfies the boundary condition of our problem. So our problem delta u equals 0 in D, and u on gamma equals G. So D equals D1 plus union D1 and D2. Gamma equals gamma 1 union gamma 2. Next, we do the following thing. Define u1 of x equals the following. First of all, in D1, the whole domain, here we have the boundary condition G, and here we take the function u0 on this domain. Yeah? So let me draw this picture. So here we have the function u0. So let me draw G1 equals G on gamma 1 and u0 on gamma 1 prime. So here it is G, here is u0, and then solve the equation here in D1. u1 equals 2 over r1 integral over u1, let me write, u1 of x equals integral over gamma 1 union gamma 1 prime g1 of y h of h1 of xy dy dsy in d1, and u0 in d2 minus d1. So we solve the problem here only in this ball and remain and leave it as it was here. So what we reach, the function u1, here it has the boundary value u0, yes, u0 on gamma 1 prime, and here it is g. Function, if we'll look from here, it is u0. In particular, it has boundary value u0. So all in all, what we have, u1 in C of D. Yes, it is continuous function. Here it has no discontinuity on one hand. On the other hand, if you solved the Dirichlet problem and replaced this function by harmonic function with the same boundary condition, then we have that integral Dirichlet over this part reduce it. Yes, it could not increase, it just decrease it. Integral Dirichlet on this part remain the same because it is the function did not change it. So after all, f of u1 is less or equal f of u0. In fact, if the function u0 was not already harmonic here, then it really is smaller. F u1 equals f of u0 only if Laplacian u0 in d1 equal 0. So if the function was harmonic in this part, then it already is solution of the same Dirichlet problem in this ball. So the functional did not change. Otherwise, it decreases. Otherwise, f of u1 is less than f of u0. So it is one step. Next step, you can guess, is the following. We consider now this second ball, d2, and we define g2 equals g on gamma 2, it is here, u1 on gamma 2 prime, it is here. Yeah, so we have this picture. This time we solve the Dirichlet problem in the ball B d2. Yes, and so we define u2 of x equals u1 of integral over gamma 2 union gamma 2 prime of g2 of y h2 of x y dsy in d2 here, and u1 in d1 minus d2 here. Yeah, so we fixed value of u on this part of the boundary. Here it is given initially, and then we minimize with the Dirichlet integral over this part. Yeah, and again delta u2 equal 0 in d2 here. Yes, and so this means that f of u2 is less or equal than f of u1, because we reduced the value of integral of square of gradient of u in this part and did not change it here. So all in all it decreased. Now then we repeat this construction. So we define we consider this, and take the function g3 equals of y, g of y on gamma 1, and u2 of y on gamma 2 here. And then we solve the Dirichlet problem here, and we write u3 of x equals integral over gamma 1 union with gamma 2 g3 of y, h1 relates to this ball, h1 of xy dsy in b1 and u2 in b2 minus b1. Yes? And again, f of u3 is less or equal than f of u2. So every time we decrease, and it is equal again only if this function u2 was harmonic here. And so we go down, down, down. And there is a limit. I don't prove the existence of the limit. I give just the procedure. Yes. So the theorem, which I don't prove because you are, I think, overburdened with proofs. If you proceed this process infinitely, then theorem, there exists limit un of x in D, n goes to infinity, and equals u of x, x in D, and u of x is harmonic. So we have harmonic function, and this satisfying initial condition u on the boundary gamma 1 union with gamma 2 equals g, given function. So this way we approach. It is a rather efficient method. It converges like geometric progression. Okay, so we now we are able to do it with union of two balls. It may be, they may have different radii, and now we can add here another ball, for example, like this. Yes, and repeat this same method. So we can solve equation in these two, the union of these two balls. Yes, fixing. We start from initial function given in their union, and then we will say reduce the Dirichlet integral first in this ball, then in this ball, then in this ball. Yes, or better, first in the union of these two balls. We can refer to the previous operation and a previous part, and we are sure that there exists harmonic function in the union of these two balls with given prescribed boundary values. So here is boundary values which were prescribed from the beginning, and boundary values here are given by some initial function u0. After we did it here, we minimize the Dirichlet integral here in this ball, u-ball. And we can repeat it again and again. So if you consider any finite union of balls of different radii, yes, then we can, repeating this procedure, solve the Dirichlet problem in this ball. And now if you have arbitrary domain D, we say cover it with some number of balls, for example like this. Yes? Okay, finite number of balls, and solve them. No, we have to give some boundary conditions. So the outer boundary of this domain, this is close. Let me draw it in color. So this is our domain D. This is domain D. And this domain D is covered by these balls, which approximate this domain, say, from outside. Yes. So we somehow transfer the boundary conditions which were initially given on the boundary of D. We transfer them on this outer boundary of this domain made of the balls, solve the Dirichlet problem for this, and then take the family of these domains made of balls, which approximate our domain D better and better. And the limit of this procedure, limit of these functions, will be solution of the Dirichlet problem. So you can see that it is really multi-step procedure. One of the first such constructions in analysis, now they are abundant. It is called alternating method, proposed by Schwarz. No, it is one of the first and classical methods of solution of the Dirichlet problem. It is funny that such methods now are called domain decomposition, and they are used extensively in today's numerical analysis. Okay, so let us finish with the Laplace equation, and next time we will start different topic. For now, have a good time. Bye.